Today, let's talk about a peculiar number. So, without further ado, let's begin our story with the A4 paper that we all know and use. If you look up the dimensions of A4 paper, you'll find that it measures 210 by 297 millimeters. Have you ever wondered why it has these particular dimensions? You might think it's arbitrary, but that's far from the case. The dimensions of A4 paper set the standard for much of modern printing, from book sizes to printer dimensions. Global standards are key here. One of the major characteristics of the industrial era is standardization. In the 1920s, the Germans created their industrial standard system, known as DIN, Deutsches Institut für Normung. This standard quickly spread worldwide and was incorporated into ISO 216. According to this standard, paper sizes are categorized into A, B, and C series. The A4 paper we often use falls under the A series. To produce these paper sizes, a large sheet is first processed, then folded and cut to produce smaller sizes. The 4 in A4 represents that it is obtained by folding and cutting the largest sheet in the A series, A0, 4 times. So, the size of A4 paper is determined by that of A0 paper. But that doesn't answer our initial question. Why is the size of A0 paper 841 by 1189 millimeters? First off, paper has a key metric known as grammage, which indicates the thickness of the paper. However, measuring thickness is difficult in practice. Therefore, the international standard uses an alternative method. It measures the weight of a square meter of paper. For simplification, A0 paper has an area of exactly 1 square meter, which makes it straightforward to determine grammage. Now, all that's left is to determine the dimensions. If you had to define a 1 square meter paper, you might naturally think of making it 1000 by 1000 millimeters. Fold that in half, and you get 1000 by 500 millimeters for A1 size, and if you fold that, you'll get 500 by 500 millimeters for A2 size. While this makes sense, it poses problems in practical usage, like when you want to scale down an image from A3 to A4. The aspect ratio changes, leading to issues like white borders or stretched images. How can we solve this? We need the paper's aspect ratio to remain constant even after it's folded and cut. The solution is straightforward and can be solved with elementary math. Imagine a rectangle with a longer side A and a shorter side B. When folded, the smaller rectangle has a longer side B and a shorter side A2. For the aspect ratios to be consistent, AB must equal 2BA. Solving this equation, we find that AB must be the square root of 2. And there you have it. The curious reason behind why the dimensions of A0 paper, and consequently A4 paper, are what they are. The aspect ratio is the square root of 2, a number that you can easily find with a calculator. The numerical value of the square root of 2 is approximately 1.4142135623731, an irrational number that never ends. This ratio is closely related to the dimensions of the A-series paper sizes. From A0, which is 841 by 1189 millimeters, to A4, which is 210 by 297 millimeters, the ratio of the dimensions is approximately 1.414. This magic ratio effortlessly resolves the issue of scaling drawings across different paper sizes. If you have a sheet from the A series, you can easily create any size in that series. While the square root of 2 is an infinite, non-repeating decimal, practical applications usually use an approximation. You might think that there's nothing special about this number. However, its discovery actually led to considerable controversy and even deaths in ancient times. If you're still with me and find this boring, buckle up. The story is about to get interesting. Around 500 BCE, there was a brilliant man named Pythagoras, who you probably know from the Pythagorean theorem, which states that the square of the hypotenuse is equal to the sum of the squares of the other two sides in a right-angled triangle. Pythagoras was so thrilled about proving this theorem that legend has it he sacrificed 100 oxen to the gods. He founded a religious cum mathematical sect called the Pythagorean school, which had some quirky rules like not eating beans and not stirring fire with iron. Dressed in white robes and a golden crown, Pythagoras taught his disciples as if he were a religious guru. Philosopher Heraclitus said of him, "Pythagoras, son of Nisarchus, practiced inquiry more than any other man, and having selected these treatises, claimed for his own wisdom what was but a knowledge of many things and an art of mischief." The school believed that numbers were the ultimate reality and that the universe could be fully described by integers or ratios of integers. Beyond that, there was nothing. Before dismissing this as ancient nonsense, note that even today, science increasingly suggests that the universe might indeed be mathematical in nature. But let's return to our story for now. Pythagoras and his school were convinced that integers and ratios of integers could fill the entire number line. Imagine a number line from negative infinity to positive infinity, punctuated by integers like -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. Next, add fractions with denominators like 2, 4, 8, and so on. These fractions would increasingly fill the gaps, and given any two fractions, one could always find a more precise ratio of integers to insert between them. For example, between 1/7 and 2/7, you could insert 3/14. Thus, the Pythagorean school firmly believed in the philosophy that the world is made up of integers and ratios of integers. You might be thinking that the views you've heard so far make sense, but in reality, they are far from accurate. Pythagoras had a student named Hippasus, an inquisitive young man good at observation, analysis, and critical thinking. One day, he asked Pythagoras about the length of the diagonal of a square with side lengths of 1. Pythagoras was stumped. According to his theorem, the square of the diagonal of a square with side lengths of 1 should be 2. But what number, when squared, equals 2? Pythagoras couldn't find an answer, and this question fundamentally shook the very foundation of his teachings. Unable to explain this anomaly, Pythagoras, fearing the collapse of his entire school of thought, chose the wrong path. He ordered a cover-up and forbade Hippasus from researching or discussing the matter further. Oppressed, Hippasus felt tormented but believed that the square root of 2 existed objectively. His teacher's theories failed to explain it, indicating a flaw in the system. Hippasus eventually spread his findings, causing an uproar in the Pythagorean school and infuriating Pythagoras, who considered him a traitor and decided to punish him. Upon hearing the news, Hippasus fled by sea but was pursued and captured. He was thrown into the endless ocean, sacrificing his life for knowledge. People later termed the kind of number discovered by Hippasus as irrational numbers, in contrast to the rational numbers, that are the ratios of integers, as initially posited by Pythagoras. It was later proven that not only do irrational numbers exist, but they also far outnumber rational numbers. It's been rigorously proven that if you were to randomly pick a number between 0 and 1, you'd almost certainly pick an irrational number. Now, what exactly is the square root of 2? While our intuition may suggest that we can get infinitely close to it using fractions, no matter how precise we get, we can only approximate the square root of 2. We can say it's roughly 1.414, but that's not entirely accurate. Even if you could draw a perfect square with side lengths of 1, you couldn't accurately measure its diagonal. Over time, mathematical advances provided various methods to approximate the square root of 2, revealing it as an infinitely non-repeating decimal. All fractions are either terminating or repeating decimals, while all irrational numbers are non-repeating. This quality of being infinite yet non-repeating is truly bizarre. Geometrically, it occupies a definite point on the number line but eludes precise numerical representation, almost like it's continually running away from us. With the advent of calculus in the mid-19th century, the mystery surrounding irrational numbers started to unravel. By then, mathematics had moved far from intuitive understandings. The idea of continuity introduced through calculus was fundamentally different from the idea of inserting fractions between numbers, which treats the number line as a string of beads, no matter how small. Much like in movies and comics where defeating one boss reveals a bigger one, the understanding of irrational numbers through calculus unleashed another monster, Pi, the ratio of a circle's circumference to its diameter. Pi is also an infinitely non-repeating decimal, another irrational number. Yet, our understanding of pi has been far slower than that of the square root of 2. It took humanity 3,000 years to confirm that pi is irrational. As early as 1650 BC, Egyptians approximated it as 3.16 using the ratio 16/9. Around 300 BC, Archimedes used 22/7, roughly 3.14, to approximate pi. Earlier, we discussed the easy calculations for the square root of 2, which has been accurately computed since over 2 millennia ago. However, it took over 500 years to refine the value of pi from 3.14 to 3.1416. One significant difference between the two is that the square root of 2 is a solution to the equation x squared equals 2. In contrast, a German mathematician named Lindemann proved in 1882 that pi is not the root of any algebraic equation with integer coefficients. In layman's terms, you can't express pi as a solution to a simple equation. So, besides irrational numbers, which can't be expressed as a fraction of two integers, we have numbers like pi that can't even be expressed by any algebraic equation. These are called transcendental numbers. Both Eastern and Western mathematicians historically used inscribed and circumscribed polygons to approximate pi, increasing the number of sides to get closer to the actual value. Later on, pi was better approximated through limits of sequences, like the Leibniz formula. Nowadays, thanks to computer programs, we've calculated pi to a staggering 60 trillion decimal places. Practically, even 40 decimal places are more than sufficient for any calculations related to the universe's size, right down to the atomic level. So, why the obsession with calculating pi to so many decimal places? There's a hypothesis in the mathematical community that pi might be a normal number, a number whose decimal expansion contains every possible finite sequence of numbers. This notion is popularized by various cultural references, such as the TV show Person of Interest, which suggests that pi contains all possible combinations of numbers, your social security number, your birthday, and even every story you'll ever tell. Though pi's normality isn't proven, its digits have been calculated and stored up to 200 million places, and you can search for any string of numbers within that data. This has led to some tongue-in-cheek discussions about data storage methods that would theoretically use the pi sequence to locate any piece of information, a concept humorously explored through a fictional file system called PIFs. The story of mathematics isn't one of abstract concepts invented to torture students. It's a story of humanity continually expanding its toolbox to solve ever more complex problems. From integers to fractions, from rational to irrational, and then to transcendental numbers, and even to imaginary numbers and calculus, each new crisis in understanding has led to the development of new mathematical tools. The journey through the history of math is a thrilling and enlightening one, reflecting not just the evolution of numbers but also our increasingly complex understanding of the world.